Picture this, a bustling city floating in the vast emptiness of space, where people walk, work, and live just as they do on Earth. But here's the catch: there's no ground beneath their feet, no natural gravity to keep them anchored. Instead, they rely on ingenious technologies to create the sensation of gravity, allowing them to thrive in an environment that defies everything we know about life on our home planet. This isn't science fiction anymore. It's the future we're building, and artificial gravity is at the heart of it. Why does this matter? Imagine spending months or even years in space, where the absence of gravity wreaks havoc on the human body. Muscles weaken, bones deteriorate, and even the way blood flows changes. Without gravity, long-term space habitation becomes a health hazard, not just a logistical challenge. That's where artificial gravity steps in, offering a way to mimic Earth's pull and make life in space not just possible but sustainable. In this video, we're diving into 20 groundbreaking solutions that could redefine how we live among the stars. From spinning space stations to futuristic nanotechnology, each idea pushes the boundaries of what's possible, bringing us closer to a future where space is no longer a frontier but a home. So, buckle up, this journey is about to take off, and by the end, you'll see just how close we are to turning this vision into reality. Let's explore the innovations that could make artificial gravity the cornerstone of humanity's next giant leap. Now let's dive into our first solution: rotating space stations. Imagine a massive structure spinning in the void of space, creating the sensation of gravity through sheer motion. This isn't just a wild idea, it's a concept grounded in physics, specifically centrifugal force. When a space station rotates, everything inside it gets pushed outward against the walls, mimicking the pull of gravity we feel on Earth. It's like being on a merry-go-round where the faster it spins, the stronger the force pushing you outward. One of the most famous designs for this kind of station is the Stanford Torus, a donut-shaped habitat that could house thousands of people. Picture a giant ring over a mile in diameter, spinning steadily to create artificial gravity along its inner surface. People would live and work on the inside of the ring, with their feet firmly planted on the ground, or rather, the floor of the station. Another groundbreaking design is the O'Neill cylinder, named after physicist Gerard O'Neill. This cylindrical habitat would be even larger, with two massive tubes rotating in opposite directions to balance each other out. Inside, you'd find entire landscapes, mountains, rivers, and even cities, all designed to feel as natural as Earth. But while these ideas are awe-inspiring, they come with their own set of challenges. Building something this massive in space would require unprecedented engineering and resources. The materials needed to construct these stations would have to be incredibly strong yet lightweight, and transporting them into orbit would be a logistical nightmare. Plus, maintaining the rotation over long periods without mechanical failures would be critical. Despite these hurdles, rotating space stations remain one of the most promising solutions for artificial gravity. They offer a way to create a stable, Earth-like environment in space, making long-term habitation not just possible but comfortable. As we continue to push the boundaries of space exploration, these spinning habitats could very well become the foundation of our future among the stars. Next up, we'll explore another fascinating approach: tether systems, where two spacecraft are connected and spun to create gravity. Stay tuned to see how this innovative idea could revolutionize space travel. Now let's shift our focus to another ingenious solution: tether systems. Picture this: two spacecraft connected by a long, sturdy cable, spinning around each other in the vastness of space. This simple yet brilliant setup can create artificial gravity through the same principle we've seen before: centrifugal force. As the two spacecraft spin, the cable keeps them tethered, and the outward push generated by their rotation mimics the pull of gravity. It's like holding two ends of a rope and spinning in circles. The faster you go, the stronger the force pulling outward. the physics behind tether systems is both elegant and practical. By adjusting the length of the cable and the speed of rotation, engineers can control the level of artificial gravity experienced inside the spacecraft. This flexibility makes tether systems an attractive option for future missions, especially those involving long-duration space travel. Imagine astronauts living and working in a spacecraft where they can walk, eat, and sleep just as they would on Earth, all thanks to this spinning tether setup. One of the most exciting applications of tether systems is their potential use in missions to Mars and beyond. For example, a spacecraft traveling to the Red Planet could deploy a tether system during the journey, providing artificial gravity for the crew. This would help counteract the negative effects of prolonged weightlessness, such as muscle atrophy and bone density loss, ensuring astronauts arrive at their destination in peak physical condition. But tether systems aren't just limited to interplanetary travel. They could also be used in smaller-scale missions, such as satellite maintenance or space station construction. By creating temporary artificial gravity, tether systems could make these tasks safer and more efficient, allowing astronauts to work in a more Earth-like environment. Of course, there are challenges to consider. The cable itself would need to be incredibly strong and resistant to wear and tear, as any failure could jeopardize the entire system. Additionally, coordinating the spin and maintaining stability over long periods would require precise engineering and constant monitoring. Despite these hurdles, tether systems represent a promising and versatile approach to artificial gravity. They offer a relatively simple and cost-effective solution compared to massive rotating space stations, making them a practical option for a wide range of space missions. As we continue to explore the cosmos, tether systems could play a crucial role in ensuring the health and well-being of astronauts, paving the way for humanity's future among the stars. Next, we'll take a closer look at another fascinating method, linear acceleration, where constant thrust from engines creates gravity-like effects. Stay tuned to discover how this approach could transform long-term space habitation. Now, let's explore another intriguing approach to artificial gravity, linear acceleration. Imagine a spacecraft steadily moving forward, propelled by engines that maintain a constant thrust. This continuous push creates a force that mimics gravity, allowing astronauts to experience a sense of weight inside the craft. It's similar to how you feel pressed against your car seat when it accelerates, except in space. This effect can be harnessed to simulate Earth-like gravity. The concept of linear acceleration is rooted in basic physics. When a spacecraft accelerates, everything inside it is pushed in the opposite direction of the thrust, creating a force that feels like gravity. The faster the acceleration, the stronger this force becomes. For example, if a spacecraft were to accelerate at a rate of 9.8 meters per second squared, the same as Earth's gravity, astronauts inside would feel as though they were standing on solid ground. One of the key advantages of this method is its simplicity. Unlike rotating structures or tether systems, linear acceleration doesn't require complex spinning mechanisms or cables. Instead, it relies on the spacecraft's engines to generate the necessary thrust. This makes it an appealing option for missions where space and weight are at a premium, such as long-duration voyages to distant planets. However, there are significant challenges to consider. Maintaining constant acceleration over long periods would require an enormous amount of fuel, making it impractical with current propulsion technologies. For instance, a trip to Mars using linear acceleration would demand far more energy than traditional methods, raising questions about feasibility and cost. Energy efficiency is another hurdle. While advancements in propulsion systems such as ion drives or nuclear engines could potentially make linear acceleration more viable, these technologies are still in their early stages. Until then, the energy demands of this approach remain a major obstacle for its widespread use in space habitats. Despite these limitations, linear acceleration holds promise for specific applications. For example, it could be used during critical phases of a mission, such as takeoff or landing, to provide temporary artificial gravity. This would help mitigate the effects of weightlessness on astronauts' bodies, reducing the risk of muscle and bone loss during extended space travel. As we look to the future, linear acceleration could become a valuable tool in our quest to create sustainable space habitats. While it may not be the ultimate solution, its potential to complement other artificial gravity methods makes it a fascinating area of exploration. Next, we'll dive into a more hands-on solution: magnetic boots and clothing, and how they could help astronauts stay grounded in microgravity environments. Stay tuned to uncover how this innovative technology could revolutionize life in space. Now, let's shift our focus to a more hands-on and practical solution for artificial gravity: magnetic boots and clothing. Picture this: astronauts floating effortlessly in a spacecraft, but with a simple twist, they can anchor themselves to the floor or walls using specially designed magnetic gear. This innovative approach offers a unique way to simulate gravity without the need for large, spinning structures or constant acceleration. Magnetic boots and clothing work by utilizing magnetic fields to create a connection between the astronaut and the metallic surfaces of the spacecraft. By wearing boots or suits embedded with magnets, astronauts can effectively stick to the floor, giving them a sense of stability and grounding. This not only makes everyday tasks like walking, eating, and working easier, but also helps reduce the disorienting effects of weightlessness. One of the biggest advantages of this method is its simplicity and adaptability. Unlike other artificial gravity solutions, magnetic gear doesn't require complex engineering or massive energy inputs. It's a lightweight, portable solution that can be easily integrated into existing spacecraft designs. For short-term missions or specific tasks, this technology could be a game changer, allowing astronauts to move more naturally and efficiently in microgravity environments. However, magnetic boots and clothing do come with their own set of limitations. For starters, they only provide localized gravity-like effects. While astronauts can anchor themselves to surfaces, the rest of their bodies remain weightless, which doesn't fully address the health risks associated with prolonged exposure to microgravity, such as muscle atrophy and bone density loss. Additionally, the reliance on metallic surfaces means this solution isn't universally applicable. Non-metallic areas of a spacecraft wouldn't support the magnetic connection. Another challenge is the potential for discomfort or restricted movement. Wearing magnetic gear for extended periods could lead to fatigue or strain, especially if the magnets are too strong or the design isn't ergonomic. Balancing the strength of the magnetic field with user comfort is a key consideration for engineers developing this technology. Despite these challenges, magnetic boots and clothing represent a promising step toward making life in space more manageable. They could be particularly useful for specific tasks such as repairs or experiments where stability is crucial. And as technology advances, we might see more sophisticated designs that address current limitations, making this solution even more effective. As we continue our journey through artificial gravity solutions, our next stop takes us to centrifugal habitats, smaller-scale rotating modules that could revolutionize short-term space missions. Stay with us to discover how these compact designs could offer a balance between practicality and health benefits for astronauts. Now, let's take a closer look at another fascinating approach to artificial gravity: centrifugal habitats. Imagine stepping into a compact, rotating module within a spacecraft where the spin creates a force that mimics gravity. These smaller-scale designs are not only practical, but also hold significant promise for short-term missions and the well-being of astronauts. Centrifugal habitats work by spinning a section of the spacecraft, generating a centrifugal force that pushes objects outward, creating a gravity-like effect. Unlike massive rotating space stations, these modules are designed to fit within existing spacecraft, making them a more feasible option for missions where space and weight are at a premium. For example, a rotating sleeping pod could allow astronauts to rest in a gravity-like environment, helping to counteract some of the negative effects of prolonged weightlessness. One of the standout advantages of centrifugal habitats is their potential to improve astronaut health. In microgravity, the human body undergoes significant changes, such as muscle loss and bone density reduction. By spending time in a rotating module, astronauts could experience partial gravity, which might help mitigate these effects. Even a small amount of gravity could make a big difference in maintaining physical health during missions. Another benefit is the flexibility these habitats offer. They can be designed to rotate at different speeds, allowing for adjustable gravity levels depending on the needs of the mission or the preferences of the crew. For instance, a higher rotation speed could simulate Earth-like gravity, while a slower spin might provide just enough force to make daily tasks easier without overwhelming the astronauts. However, centrifugal habitats aren't without their challenges. The spinning motion can cause dizziness or disorientation, especially when transitioning between the rotating module and the rest of the spacecraft. Engineers are working on solutions to minimize these effects, such as designing smooth transition zones or incorporating visual cues to help astronauts adapt. Despite these hurdles, centrifugal habitats represent a practical and innovative step toward making space travel more sustainable and comfortable. They could be particularly valuable for missions to the Moon or Mars, where astronauts might need to spend extended periods in low-gravity environments. By providing a controlled gravity experience, these modules could help ensure that astronauts arrive at their destination in peak physical condition. As we continue exploring artificial gravity solutions, our next stop takes us to the concept of variable gravity zones, spaces within a habitat where astronauts can experience different levels of gravity. Stay tuned to learn how this idea could revolutionize both health and research in space. Now, let's shift our focus to an intriguing concept that could redefine how astronauts experience gravity in space: variable gravity zones. Picture a habitat where different sections offer varying levels of gravity, allowing astronauts to move between environments that simulate Earth-like conditions, lunar gravity, or even the weightlessness of deep space. This innovative approach could have profound implications for both human health and scientific discovery. Variable gravity zones work by designing specific areas within a habitat to generate different gravitational forces. For example, one section might rotate faster to create Earth-like gravity, while another rotates more slowly to mimic the Moon's lighter pull. This flexibility allows astronauts to tailor their environment based on their needs, whether it's for physical recovery, exercise, or conducting experiments. One of the most exciting benefits of this system is its potential to improve astronaut health. Prolonged exposure to microgravity can lead to muscle atrophy, bone density loss, and even changes in vision. By spending time in zones with higher gravity, astronauts could counteract these effects, maintaining their strength and overall well-being. Imagine a workout area with Earth-like gravity where astronauts can exercise effectively, followed by a low-gravity zone for rest and recovery. But the advantages don't stop at health. Variable gravity zones could also revolutionize scientific research in space. Scientists could study how different gravitational forces affect everything from plant growth to fluid dynamics, opening up new avenues for discovery. For instance, experiments in lunar gravity could help us prepare for future missions to the Moon, while studies in microgravity could deepen our understanding of fundamental physics. Of course, designing such a habitat comes with its own set of challenges. Creating distinct gravity zones requires precise engineering to ensure smooth transitions between areas. Astronauts would need to adapt quickly to changing gravitational forces, which could initially cause disorientation or discomfort. Engineers are exploring solutions like gradual transition corridors and visual cues to help astronauts adjust seamlessly. Despite these hurdles, the potential of variable gravity zones is immense. They could serve as a versatile tool for both short-term missions and long-term space habitation, offering a customizable environment that supports both human health and scientific progress. As we continue to push the boundaries of space exploration, this concept could play a key role in making life beyond Earth not only possible but also sustainable. Next, we'll dive into another fascinating idea: gravity-assist spacecraft, which could create temporary artificial gravity during long journeys through space. Stay tuned to discover how this technology might shape the future of interplanetary travel. Now, let's explore a concept that could transform the way we experience gravity during long space journeys: gravity-assist spacecraft. Imagine a spacecraft designed not just to travel through space but to create temporary artificial gravity for its crew. This idea leverages the principles of gravity-assist maneuvers, a technique already used in space exploration, but with a twist to enhance the comfort and health of astronauts. Gravity-assist maneuvers typically involve using the gravitational pull of a planet or moon to slingshot a spacecraft, increasing its speed without expending extra fuel. But what if we could use this same principle to generate artificial gravity inside the spacecraft? By carefully planning the trajectory and rotation of the spacecraft, engineers could create a centrifugal force that mimics gravity, even if only temporarily. This approach could be particularly valuable for missions to Mars and beyond. During long voyages, astronauts face the challenges of microgravity, which can weaken muscles, reduce bone density, and even affect their vision. Temporary artificial gravity could provide a much-needed break from these effects, allowing astronauts to exercise, eat, and rest in an environment that feels closer to Earth. For example, a spacecraft could be designed with a rotating section that spins during specific phases of the journey, such as when passing near a planet. This rotation would generate a gravity-like force, giving astronauts a chance to stretch their legs and move more naturally. Once the maneuver is complete, the spacecraft could return to its standard configuration, conserving energy for the rest of the mission. The benefits of this system extend beyond physical health. Temporary artificial gravity could also improve the psychological well-being of astronauts. Living in microgravity for months or even years can be mentally taxing, and the ability to experience gravity, even briefly, could provide a sense of normalcy and comfort. Of course, implementing this technology comes with challenges. Designing a spacecraft with rotating sections requires careful engineering to ensure stability and safety. Astronauts would need to adapt to the changing forces, and the spacecraft systems would have to handle the additional stress of rotation. However, with advancements in materials and propulsion technology, these hurdles are not insurmountable. Gravity-assist spacecraft represent a promising step toward making long-term space travel more sustainable and humane. By integrating temporary artificial gravity into future missions, we could protect the health and morale of astronauts, paving the way for humanity's exploration of Mars and beyond. Next, we'll turn our attention to another innovative solution: gyroscopic systems, which could offer a unique way to generate artificial gravity in space habitats. Stay tuned to learn how spinning gyroscopes might revolutionize life beyond Earth. Now, let's shift gears and explore a fascinating concept that could redefine how we create artificial gravity in space: gyroscopic systems. Picture a gyroscope, a spinning wheel or disc that maintains its orientation due to angular momentum. Now, imagine harnessing that same principle to generate gravity-like forces within a spacecraft or habitat. This idea might sound like science fiction, but it's rooted in solid physics and could offer a unique solution for future space missions. Gyroscopic systems work by spinning a mass at high speeds, creating a force that resists changes in orientation. If applied strategically within a space habitat, this spinning motion could produce a centrifugal force that mimics gravity. For example, a spacecraft could be equipped with a large gyroscopic module that spins at a controlled rate, generating a gravity-like pull along its outer edges. Astronauts inside this module would feel a force pushing them toward the floor, allowing them to walk, exercise, and perform tasks as they would on Earth. One of the key advantages of gyroscopic systems is their compact design. Unlike massive rotating space stations, gyroscopes can be integrated into smaller habitats or even individual modules within a spacecraft. This makes them a practical option for missions where space and weight are at a premium, such as lunar bases or Mars-bound vehicles. Additionally, gyroscopic systems could be adjusted to create different levels of artificial gravity, allowing astronauts to experience varying forces depending on their need. For instance, higher spin rates could simulate Earth-like gravity, while slower rates might provide a gentler environment for recovery or research. The potential applications of gyroscopic systems extend beyond just physical health. By providing a stable, gravity-like environment, these systems could also enhance the psychological well-being of astronauts. Living in microgravity for extended periods can be disorienting and stressful, but a gyroscopic habitat could offer a sense of normalcy and stability. Imagine being able to sit down for a meal, take a walk, or even sleep in a bed that feels grounded. These small comforts could make a big difference during long missions. Of course, there are challenges to consider. Designing a gyroscopic system that's both efficient and safe requires precise engineering. The spinning components must be carefully balanced to avoid vibrations or instability, and the system must be robust enough to withstand the rigors of space travel. Energy consumption is another factor, as maintaining high spin rates over long periods could demand significant power. However, with advancements in materials science and energy-efficient technologies, these obstacles are becoming more manageable. Gyroscopic systems represent an exciting frontier in the quest for artificial gravity. By leveraging the principles of angular momentum, we could create habitats that not only protect astronauts' health but also enhance their quality of life in space. As we continue to push the boundaries of space exploration, innovations like these will be essential for making long-term habitation beyond Earth a reality. Next, we'll delve into another groundbreaking idea: electromagnetic fields and their potential to simulate gravity in space. Stay tuned to discover how invisible forces could shape the future of space habitats. Now, let's turn our attention to a concept that feels like it's straight out of a sci-fi novel: electromagnetic fields as a potential solution for artificial gravity. While it might sound futuristic, the idea of using invisible forces to mimic gravity is grounded in real science, and it opens up a world of possibilities for future space habitats. At its core, this concept relies on the principles of electromagnetism, one of the fundamental forces of nature. Electromagnetic fields are created by moving electric charges, and they can exert forces on other charged objects. The idea here is to use these fields to create a force that acts like gravity, pulling objects or people toward a surface. Imagine a spacecraft equipped with powerful electromagnetic generators that produce a field strong enough to simulate Earth-like gravity. Astronauts inside could walk, work, and live as if they were on solid ground, all thanks to the invisible push and pull of these fields. One of the most intriguing aspects of this approach is its potential for precision. Unlike rotating systems or tethers, electromagnetic fields could be finely tuned to create specific levels of artificial gravity. This means astronauts could experience different gravitational forces depending on their needs: higher gravity for exercise and bone health, or lower gravity for recovery and relaxation. Additionally, electromagnetic systems could be turned on and off as needed, offering flexibility that other methods might lack. However, there are significant challenges to overcome. For one, generating electromagnetic fields strong enough to simulate gravity would require an enormous amount of energy. current technology simply isn't advanced enough to produce such fields efficiently, especially in the resource-limited environment of space. Energy consumption is a major hurdle, as powering these systems could drain the limited resources of a spacecraft or habitat. Moreover, the materials needed to create and sustain these fields would need to be lightweight, durable, and capable of withstanding the harsh conditions of space. Another limitation is the potential impact on human health. While electromagnetic fields are a natural part of our environment, prolonged exposure to high-intensity fields could have unknown effects on the human body. Research would be needed to ensure that these systems are not only effective but also safe for long-term use. Despite these challenges, the potential of electromagnetic fields as a gravity solution is too compelling to ignore. Advances in energy-efficient technologies and materials science could one day make this idea a reality. Imagine a future where space habitats are equipped with electromagnetic systems that provide gravity on demand, transforming the way we live and work in space. As we continue to explore the boundaries of what's possible, electromagnetic fields represent a bold and innovative approach to solving one of the biggest challenges of space habitation. Next, we'll dive into another exciting concept, artificial gravity rings and how they could revolutionize life in space. Stay tuned to uncover how rotating structures might shape the future of space exploration. Now, let's shift gears and explore a concept that has captured the imagination of science fiction fans for decades: artificial gravity rings. This idea revolves around a rotating ring or structure within a spacecraft, using centrifugal force to simulate gravity. Picture a massive circular habitat spinning steadily, creating a force that pushes everything inside toward the outer walls. For astronauts, this would feel just like standing on solid ground, even as they float through the vacuum of space. The concept of artificial gravity rings isn't just a product of creative storytelling, it's rooted in real physics. By spinning a ring-shaped structure, the centrifugal force generated would mimic the effects of gravity. The faster the rotation, the stronger the artificial gravity. This principle has been showcased in iconic sci-fi works like the rotating space station in 2001: A Space Odyssey, or the massive ring habitats in The Expanse. These depictions have inspired generations to dream about what life in space could look like. But how feasible is this idea in reality? The answer lies in the engineering challenges. To create a stable and comfortable artificial gravity environment, the ring would need to be large enough to minimize the Coriolis effect, which can cause disorientation and nausea if the rotation is too fast or the radius too small. For example, a ring with a radius of several hundred meters would allow for a slower, more natural rotation rate, reducing the risk of these side effects. However, building such a massive structure in space would require advanced materials and construction techniques that are still in development. Another consideration is the energy required to keep the ring spinning. While the initial rotation could be achieved with thrusters or other propulsion systems, maintaining that motion over long periods would demand a reliable and efficient power source. Solar energy or nuclear reactors could be potential solutions, but each comes with its own set of challenges and limitations. Despite these hurdles, artificial gravity rings hold immense promise for future space habitats. They could provide a stable, Earth-like environment for long-term missions, reducing the health risks associated with microgravity, such as muscle atrophy and bone loss. Imagine a space station where astronauts can exercise, sleep, and work under conditions that closely resemble life on Earth, all while orbiting distant planets or traveling between stars. As we look to the future, artificial gravity rings represent a bold step toward making space habitation more sustainable and comfortable. While the technology to build them may still be on the horizon, the concept continues to inspire scientists and engineers to push the boundaries of what's possible. Next, we'll delve into an even more speculative idea: gravity-inducing drugs and how they might revolutionize life in space. stay tuned to uncover how medicine could play a role in overcoming the challenges of microgravity. Now, let's take a fascinating leap into the realm of speculative science with a concept that could redefine how we experience gravity in space: gravity-inducing drugs. Imagine a future where astronauts no longer need massive rotating structures or complex machinery to simulate gravity. Instead, they could simply take a pill or undergo a treatment that tricks their bodies into feeling the effects of gravity, even in the weightlessness of space. This idea might sound like science fiction, but it's a topic that's gaining traction among researchers exploring innovative ways to combat the challenges of microgravity. The human body is incredibly sensitive to the absence of gravity. Prolonged exposure to microgravity can lead to muscle atrophy, bone density loss, and even changes in cardiovascular function. Traditional solutions like exercise routines and resistance training help mitigate these effects, but they don't fully replicate the conditions of Earth's gravity. This is where gravity-inducing drugs come into play. The idea is to develop pharmaceuticals or treatments that could stimulate the body's systems to respond as if gravity were present. For example, such drugs might target the musculoskeletal system, encouraging muscle growth and bone regeneration, or influence the vestibular system to reduce the disorientation often experienced in zero gravity. One potential approach involves leveraging our understanding of how the body senses and adapts to gravity. Scientists are exploring the role of mechanosensitive cells, which respond to physical forces like pressure and tension. By developing drugs that activate these cells or mimic their responses, it might be possible to create a biological simulation of gravity. Another avenue is gene therapy, where specific genes responsible for muscle and bone maintenance could be targeted to counteract the effects of microgravity. While these ideas are still in the early stages of research, they represent a bold new frontier in space medicine. Of course, the development of gravity-inducing drugs raises important ethical questions. For instance, what are the potential side effects of long-term use? Could these treatments have unintended consequences on the body's natural processes? And how would we ensure equitable access to such advanced medical technologies, especially as space exploration becomes more accessible to private entities and nations? These are critical considerations that must be addressed as we move forward. Despite the challenges, the potential benefits are immense. Gravity-inducing drugs could revolutionize long-term space habitation, making it safer and more sustainable for astronauts. They could also have applications here on Earth, helping individuals with conditions like osteoporosis or muscle-wasting diseases. As we continue to push the boundaries of human exploration, this speculative idea reminds us that sometimes the most groundbreaking solutions come from thinking outside the box, or in this case, outside the gravity well. Next, we'll explore another innovative approach, modular gravity systems, and how they could offer customizable solutions for future space habitats. Stay with us as we uncover how flexibility and adaptability might shape the future of living in space. Now, let's shift our focus to a concept that brings flexibility and customization to the forefront of artificial gravity: modular gravity systems. Imagine a space habitat where astronauts can adjust gravity levels to suit their needs, whether it's for work, exercise, or rest. This approach could revolutionize how we design and experience life in space, offering a level of adaptability that traditional systems simply can't match. Modular gravity systems work by creating distinct zones within a habitat, each with its own gravity settings. For example, a living area might have Earth-like gravity to make daily activities feel natural, while a laboratory could operate in microgravity to facilitate delicate experiments. Exercise zones might feature slightly higher gravity to enhance physical training, and sleeping quarters could offer lower gravity to promote restful sleep. The key here is customization. Astronauts could tailor their environment to optimize both productivity and well-being. One of the most exciting aspects of modular gravity systems is their versatility. Unlike large rotating structures or fixed designs, these systems can be reconfigured as needed. If a mission's requirements change, the habitat's gravity zones can be adjusted accordingly. This adaptability makes modular systems particularly appealing for long-term missions, where needs and priorities may evolve over time. For instance, a Mars habitat might start with higher gravity zones to help astronauts acclimate to the planet's lower gravity, then shift to different settings as the mission progresses. The technology behind modular gravity systems could involve a combination of rotating modules, adjustable centrifugal forces, and even localized magnetic fields. By integrating these elements, engineers could create a habitat that feels dynamic and responsive, rather than static and rigid. This approach not only enhances functionality, but also improves the psychological comfort of astronauts who would have more control over their environment. Of course, implementing modular gravity systems comes with its own set of challenges. Designing and building such a habitat would require advanced engineering and precise control systems to ensure safety and reliability. Energy consumption is another consideration, as maintaining multiple gravity zones could demand significant power. However, the potential benefits ranging from improved health outcomes to enhanced mission flexibility make this a promising avenue for future space exploration. As we continue to push the boundaries of what's possible in space, modular gravity systems remind us that innovation often lies in adaptability. By giving astronauts the tools to shape their environment, we're not just solving the challenges of artificial gravity, we're reimagining how humans can thrive in the cosmos. Next, we'll explore how mass distribution within a spacecraft could create gravity-like effects, offering yet another fascinating solution for future space habitats. Stay tuned as we uncover the science behind this intriguing concept. Now, let's turn our attention to a concept that takes a different approach to simulating gravity: mass distribution. Imagine a spacecraft where the careful arrangement of mass creates a gravitational pull, allowing astronauts to experience gravity-like effects without the need for spinning structures or complex machinery. This idea hinges on the principle that mass generates gravity, and by strategically positioning heavy materials within a habitat, we could mimic the sensation of being grounded. The concept of gravity through mass distribution relies on placing dense materials, such as metals or other heavy elements, in specific areas of a spacecraft. For instance, if a habitat's floor is lined with a thick layer of dense material, the gravitational pull from that mass could create a downward force similar to what we feel on Earth. This approach could be particularly useful for smaller spacecraft or habitats where rotating designs might not be practical. One of the key advantages of this method is its simplicity. Unlike rotating habitats or tether systems, mass distribution doesn't require moving parts or constant energy input. Once the heavy materials are in place, the gravitational effect would be consistent and reliable. This makes it an attractive option for long-duration missions, where minimizing mechanical complexity and energy consumption is crucial. However, there are challenges to consider. The amount of mass required to generate a noticeable gravitational effect would be substantial, potentially increasing the weight and cost of launching the spacecraft. Additionally, the distribution of mass would need to be carefully calculated to ensure an even gravitational pull across the habitat, avoiding areas where the effect might be too weak or uneven. Engineers would also need to account for the structural integrity of the spacecraft, as the added mass could place stress on its framework. Despite these hurdles, the potential applications of mass distribution are intriguing. For example, a Mars habitat could incorporate heavy materials into its design to help astronauts adjust to the planet's lower gravity. Similarly, a lunar base might use mass distribution to create a more Earth-like environment for long-term residents. This approach could also be combined with other artificial gravity solutions, such as rotating modules or magnetic systems, to create a hybrid habitat that offers the best of both worlds. As we explore the possibilities of mass distribution, it's clear that this method offers a unique and innovative way to address the challenges of artificial gravity. By leveraging the natural properties of mass, we could create environments that feel more familiar and comfortable for astronauts, paving the way for sustainable life in space. Next, we'll dive into the fascinating concept of space elevators with built-in gravity systems, a vision that could redefine how we travel and live beyond Earth. Stay with us as we uncover the science and potential of this groundbreaking idea. Now, let's shift our focus to a concept that feels like it's straight out of science fiction but could one day become a reality: space elevators with built-in gravity systems. Imagine a towering structure that stretches from Earth's surface into space, acting as a bridge to the stars. But what if this elevator didn't just transport people and cargo? It also provided artificial gravity along the way. This idea combines the practicality of space elevators with the comfort of gravity, creating a revolutionary approach to space travel and habitation. A space elevator works by using a cable anchored to Earth and extending tens of thousands of kilometers into space, with a counterweight at the far end to keep it stable. Climbers or vehicles would move up and down this cable, ferrying materials and passengers between Earth and space. Now, imagine if sections of this elevator were designed to rotate or incorporate mass distribution systems, creating artificial gravity for those inside. This would allow travelers to experience gravity during their journey, reducing the physical strain of prolonged weightlessness and making long trips more comfortable. One of the most exciting possibilities of this concept is its potential to transform how we think about space travel. Instead of enduring the harsh conditions of microgravity for days or weeks, astronauts could move through a space elevator with gravity zones, maintaining their health and well-being throughout the journey. This could be especially beneficial for missions to Mars or beyond, where the effects of weightlessness pose significant risks to human health, but the benefits don't stop at travel. Space elevators with gravity systems could also serve as habitats themselves. Imagine a rotating section of the elevator designed as a living space, complete with artificial gravity, breathable air, and all the comforts of home. This could provide a stepping stone for humanity's expansion into space, offering a place to live, work, and conduct research while still connected to Earth. Of course, the challenges of building a space elevator are immense. The materials needed for the cable would have to be incredibly strong and lightweight, capable of withstanding the stresses of Earth's gravity and the vacuum of space. Engineers would also need to design the gravity systems to function seamlessly within the elevator's structure, ensuring safety and reliability. Despite these hurdles, the potential rewards are staggering, from reducing the cost of space travel to enabling sustainable life beyond our planet. As we look to the future, space elevators with gravity systems represent a bold vision for humanity's journey into space. By combining cutting-edge engineering with innovative gravity solutions, we could create a pathway to the stars that feels as natural as stepping onto an escalator. Next, we'll explore another fascinating idea: gravity-inducing exoskeletons and how they could help astronauts stay grounded in the most extreme environments. Stay tuned as we uncover the science behind this wearable technology. Now, let's step into the realm of wearable technology with a solution that feels like it's straight out of a futuristic sci-fi movie: gravity-inducing exoskeletons. These advanced devices could revolutionize how astronauts experience life in space by simulating the effects of gravity, even in the weightlessness of microgravity environments. Picture a sleek, high-tech suit that not only supports an astronaut's body but also creates a sense of gravity, helping them stay grounded literally and figuratively. Gravity-inducing exoskeletons work by applying controlled pressure or resistance to the body, mimicking the forces we feel under gravity. For example, the suit could use mechanical actuators or pneumatic systems to gently push against the muscles and bones, creating the sensation of weight. This would help counteract the negative effects of microgravity, such as muscle atrophy and bone density loss, which are major challenges for astronauts on long-term missions. By wearing these exoskeletons during daily activities, astronauts could maintain their physical health and strength, reducing the need for extensive rehabilitation upon returning to Earth. One of the most exciting aspects of this technology is its adaptability. These exoskeletons could be customized to provide different levels of resistance, allowing astronauts to simulate Earth-like gravity or even adjust it to match the gravity of other planets like Mars. This flexibility would be invaluable for preparing astronauts for missions to different celestial bodies, ensuring they're physically ready for the unique conditions they'll encounter. But the benefits don't stop at physical health. Gravity-inducing exoskeletons could also improve mental well-being. The constant sensation of weightlessness can be disorienting and stressful, but these suits could provide a comforting sense of normalcy, helping astronauts feel more connected to Earth. Imagine slipping into an exoskeleton after a long day of work in space and instantly feeling the familiar pull of gravity. It could be a game-changer for morale and mental resilience. Of course, developing such technology comes with its own set of challenges. The exoskeletons would need to be lightweight, energy efficient, and comfortable enough to wear for extended periods. Engineers would also have to ensure they're durable enough to withstand the harsh conditions of space. But with advancements in materials science and robotics, these hurdles are becoming increasingly surmountable. As we look to the future, gravity-inducing exoskeletons could become an essential tool for space exploration, blending cutting-edge technology with human ingenuity to overcome the challenges of living beyond Earth. Next, we'll dive into another innovative idea, using fluid dynamics to create gravity-like forces in space habitats. Stay tuned as we explore how this fascinating concept could shape the future of life in space. Now, let's shift our focus to a concept that feels almost like magic: gravity through fluid dynamics. This innovative approach taps into the fascinating behavior of fluids to create forces that mimic gravity, offering a unique solution for future space habitats. Imagine a habitat where the very movement of liquids generates a sense of weight, helping astronauts stay grounded and healthy in the absence of Earth's gravity. At its core, this idea relies on the principles of fluid dynamics, which govern how liquids and gases move and interact. By carefully designing systems that manipulate fluid flow, engineers could create pressure gradients or centrifugal forces within a habitat. These forces would act on the human body, producing effects similar to gravity. For instance, a rotating cylinder filled with water could generate outward pressure, pushing astronauts toward the outer walls and simulating the sensation of weight. Alternatively, carefully controlled airflows or liquid currents could create localized gravity-like effects in specific areas of a habitat. One of the most intriguing applications of this concept is its potential to address the health challenges of microgravity. Astronauts could spend time in fluid-based environments where the forces exerted by moving liquids help maintain muscle tone and bone density. Picture a space habitat with specialized chambers where astronauts exercise or rest while immersed in fluid systems designed to replicate Earth's gravity. This could significantly reduce the physical toll of long-term space missions, making it easier for astronauts to stay healthy and productive. However, implementing gravity through fluid dynamics isn't without its challenges. Designing systems that can precisely control fluid behavior in microgravity requires advanced engineering and materials. The habitat would need to be equipped with pumps, turbines, or other mechanisms to generate and regulate fluid flow, all while ensuring the system is energy efficient and reliable. Additionally, the presence of large volumes of liquid in a space habitat introduces concerns about safety, maintenance, and the potential for leaks or spills in a zero-gravity environment. Despite these hurdles, the potential benefits make this concept worth exploring. Fluid-based gravity systems could offer a versatile and adaptable solution, allowing astronauts to experience different levels of gravity depending on their needs. For example, a habitat could feature zones with varying fluid dynamics, enabling astronauts to transition between Earth-like gravity and lower levels suitable for scientific experiments or rest. As we continue to push the boundaries of space exploration, gravity through fluid dynamics represents a bold and imaginative approach to solving one of the most fundamental challenges of living beyond Earth. Next, we'll explore how virtual reality could play a role in tricking the brain into perceiving gravity, opening up new possibilities for psychological well-being in space. Stay with us as we uncover this next frontier of artificial gravity solutions. Now, let's step into a world where the boundaries between reality and imagination blur gravity-inducing virtual reality. This cutting-edge concept leverages the power of virtual reality to create the illusion of gravity, offering a fascinating solution for future space habitats. By tricking the brain into perceiving weight and orientation, this technology could revolutionize how astronauts experience life in microgravity environments. At its heart, this idea relies on the brain's remarkable ability to adapt to sensory input. Virtual reality systems could simulate the visual and auditory cues associated with gravity, such as the sensation of standing on solid ground or the pull of a downward force. For example, a VR headset paired with motion tracking sensors could create immersive environments where astronauts feel as though they're walking on Earth, even while floating in space. This could help counteract the disorientation and spatial confusion often experienced in zero-gravity conditions. One of the most exciting aspects of gravity-inducing virtual reality is its potential to support psychological well-being. Long-term exposure to microgravity can lead to feelings of isolation, stress, and even cognitive decline. By providing astronauts with familiar gravity-like experiences, VR could offer a mental escape, reducing stress and improving overall morale. Imagine an astronaut stepping into a virtual forest, feeling the crunch of leaves underfoot, or gazing at a serene beach with waves lapping at their feet. These immersive experiences could provide a much-needed sense of normalcy and connection to Earth. However, this technology isn't without its challenges. While VR can simulate visual and auditory cues, it currently struggles to replicate the physical sensations of gravity, such as the pressure on the soles of the feet or the pull of weight on the body. Advanced haptic feedback systems and wearable devices could help bridge this gap, but they would need to be lightweight, energy efficient, and comfortable for long-term use. Additionally, prolonged use of VR could lead to motion sickness or eye strain, which would need to be carefully managed in a space habitat. Despite these limitations, gravity-inducing virtual reality holds immense promise. It could be used not only for psychological support but also for training and rehabilitation. Astronauts could practice complex tasks in a simulated gravity environment, preparing them for missions on the Moon or Mars. Similarly, VR could aid in physical therapy, helping astronauts regain strength and coordination after extended periods in microgravity. As we look to the future, gravity-inducing virtual reality represents a creative and versatile tool for enhancing life in space. By merging technology with human psychology, it offers a unique way to address the challenges of living beyond Earth. Next, we'll explore how orbital mechanics could be harnessed to create artificial gravity, opening up new possibilities for sustainable space habitats. Stay tuned as we dive into this next frontier of innovation. Now, let's shift our focus to a concept that draws from the very laws governing the cosmos, gravity through orbital mechanics. This approach taps into the natural forces at play in space, offering a potential pathway to creating artificial gravity without the need for complex machinery or energy-intensive systems. By understanding how celestial bodies interact, we can explore innovative ways to simulate gravity for future space habitats. At its core, this idea revolves around harnessing the principles of orbital motion. Imagine a spacecraft or habitat moving in a specific orbit around a planet or moon. The gravitational pull between the two bodies creates a centripetal force, which could be used to generate a gravity-like effect. For instance, a habitat in a carefully calculated orbit could experience a constant outward pull, mimicking the sensation of gravity for its inhabitants. This method relies on the same physics that keeps satellites in orbit, but with a twist, designing the orbit to benefit those living inside the habitat. One of the most intriguing aspects of this approach is its potential for sustainability. Unlike rotating structures or tether systems, which require energy to maintain motion, gravity through orbital mechanics could operate passively, leveraging the natural dynamics of space. This makes it an attractive option for long-term habitats where energy efficiency is crucial. Additionally, this method could be scaled to accommodate larger habitats or even entire colonies, providing a stable and consistent gravity environment. However, implementing this solution isn't without challenges. Designing an orbit that provides the right balance of gravitational force and stability requires precise calculations and engineering. The habitat would need to maintain its position relative to the planet or moon, avoiding deviations that could disrupt the artificial gravity effect. Furthermore, the size and shape of the orbit would need to be carefully tailored to ensure the gravitational pull is strong enough to be effective, but not so strong that it causes discomfort or health issues for the inhabitants. Despite these hurdles, the potential benefits are significant. Gravity through orbital mechanics could offer a low-energy, long-term solution for space habitats, reducing the reliance on mechanical systems and minimizing maintenance needs. It could also open up new possibilities for colonizing distant worlds where traditional artificial gravity methods might be impractical. By aligning our habitats with the natural rhythms of the cosmos, we could create environments that feel more connected to the universe around us. As we continue to explore the frontiers of space, gravity through orbital mechanics stands out as a promising and elegant solution. It reminds us that sometimes the answers we seek are already written in the stars. Next, we'll delve into the speculative yet fascinating world of nanotechnology and its potential to simulate gravity, offering a glimpse into the future of space habitation. Stay with us as we uncover this next chapter of innovation. Now, let's venture into the realm of the incredibly small yet profoundly powerful nanotechnology. This speculative yet groundbreaking approach to artificial gravity takes us beyond traditional mechanical systems and into the microscopic world of nanobots. Imagine tiny machines smaller than a grain of sand working together to create gravity-like effects within the human body. It's a concept that feels like science fiction, but with rapid advancements in nanotechnology, it might not be as far-fetched as it seems. At the heart of this idea is the potential for nanobots to interact with the human body at a cellular level. These microscopic robots could be programmed to apply precise forces to tissues, muscles, and bones, mimicking the effects of gravity. For example, nanobots could stimulate muscle fibers to counteract the muscle atrophy that occurs in microgravity environments. They could also apply gentle pressure to bones, helping to prevent the bone density loss that astronauts often experience during long-term space missions. By working in harmony with the body's natural systems, these nanobots could provide a personalized and adaptable form of artificial gravity. One of the most exciting aspects of this technology is its potential for customization. Unlike large-scale solutions like rotating habitats or tether systems, nanotechnology could be tailored to meet the specific needs of each individual. For instance, an astronaut with a higher risk of bone loss could receive a different nanobot configuration compared to someone with a focus on muscle maintenance. This level of precision could revolutionize how we approach health and wellness in space, offering a more targeted and efficient solution to the challenges of microgravity. However, the road to implementing gravity-inducing nanotechnology is filled with challenges. Developing nanobots capable of safely and effectively interacting with the human body requires breakthroughs in materials science, robotics, and medical technology. Ensuring that these tiny machines can operate without causing harm or triggering immune responses is a significant hurdle. Additionally, the energy requirements for powering and controlling nanobots on such a small scale remain a topic of ongoing research. Despite these obstacles, the potential benefits make this an area worth exploring. Beyond its applications in space, this technology could have far-reaching implications for life on Earth. Imagine using nanobots to assist patients recovering from long periods of bed rest or to help individuals with mobility issues maintain muscle and bone health. The possibilities are vast, and the lessons learned from developing gravity-inducing nanotechnology for space could pave the way for advancements in medicine and rehabilitation. As we look to the future, the integration of nanotechnology into space habitation represents a bold and innovative step forward. It challenges us to think beyond conventional solutions and explore the untapped potential of the microscopic world. While this technology is still in its early stages, its promise is undeniable. Next, we'll explore the final frontier of artificial gravity solutions, hybrid systems that combine the best of multiple approaches to create adaptable and efficient environments for future space habitats. Stay tuned as we uncover how these integrated systems could shape the future of life in space. Now, let's turn our attention to the final and perhaps most versatile solution on our list: hybrid gravity systems. Imagine a future where space habitats don't rely on just one method to simulate gravity, but instead combine the strengths of multiple approaches to create a more adaptable and efficient environment. This is the essence of hybrid gravity systems, a concept that could revolutionize how we live and work in space. At its core, a hybrid gravity system integrates two or more artificial gravity solutions to address the unique challenges of space habitation. For example, a habitat might combine the centrifugal force of a rotating module with the localized gravity effects of magnetic boots or exoskeletons. This combination could allow astronauts to experience Earth-like gravity in certain areas, while still benefiting from the flexibility of microgravity in others. Such a system would not only enhance physical health but also improve the overall functionality of the habitat, making it more versatile for scientific research, daily activities, and even recreation. One of the key advantages of hybrid systems is their adaptability. Different missions and habitats have different needs, and a one-size-fits-all approach to artificial gravity may not always be practical. By combining solutions, we can tailor gravity levels to specific tasks or environments. For instance, a Mars-bound spacecraft might use linear acceleration for long-duration travel while incorporating rotating modules for exercise and rest areas. This flexibility ensures that astronauts can maintain their health and productivity throughout the journey. Another exciting possibility is the integration of nanotechnology with larger-scale systems. Picture a habitat where nanobots work alongside rotating modules to provide personalized gravity support for each crew member. The nanobots could address individual health concerns such as muscle atrophy or bone density loss, while the rotating modules offer a consistent gravitational environment for daily activities. This synergy between macro and micro solutions could create a truly holistic approach to artificial gravity. Of course, designing and implementing hybrid gravity systems comes with its own set of challenges. Coordinating multiple technologies requires careful planning and engineering to ensure compatibility and efficiency. Energy consumption, system reliability, and safety are all critical factors that must be addressed. However, the potential benefits such as improved health outcomes, enhanced mission flexibility, and a more Earth-like living experience make this approach a compelling area of research and development. As we look to the future, hybrid gravity systems represent a bold step forward in our quest to make space habitation sustainable and comfortable. By combining the best of multiple solutions, we can create environments that not only support human health but also inspire innovation and exploration. This integrated approach could be the key to unlocking the full potential of life in space, paving the way for long-term missions and even permanent settlements beyond Earth. With that, we've explored all 20 artificial gravity solutions, each offering unique possibilities for the future of space habitats. From rotating stations to nanotechnology, these innovations remind us that the challenges of living in space are not insurmountable. They inspire us to dream bigger, push further, and imagine a future where humanity thrives among the stars. Thank you for joining us on this journey, and don't forget to share your thoughts in the comments below. If you enjoyed this video, be sure to like, subscribe, and hit the notification bell for more futuristic content. Until next time, keep looking up. As we wrap up our exploration of artificial gravity solutions, it's clear that the future of space habitation is brimming with possibilities. From the classic concept of rotating space stations to the cutting-edge potential of nanotechnology, each of the 20 solutions we've discussed offers a unique pathway to overcoming the challenges of living in microgravity. Whether it's through centrifugal force, magnetic clothing, or even gravity-inducing drugs, these innovations remind us that humanity's ingenuity knows no bounds. What's truly exciting is how these solutions could work together. Hybrid systems, for instance, show us that the future of space habitats might not rely on just one method, but instead combine multiple approaches to create environments that are both functional and adaptable. Imagine a world where astronauts can seamlessly transition from Earth-like gravity zones to microgravity areas, all within the same habitat. This level of flexibility could redefine how we live, work, and explore in space. The potential impact of these technologies goes far beyond just comfort. They could enable long-term missions to Mars, the Moon, and even distant exoplanets. They could support the growth of permanent space settlements, where future generations might thrive among the stars, and they could open up entirely new avenues for scientific discovery, allowing us to study the effects of gravity on biology, physics, and even human psychology in ways we've never imagined. As we stand on the brink of this new era, one thing is certain: the challenges of space habitation are not insurmountable. With creativity, collaboration, and a relentless drive to innovate, we can turn these futuristic ideas into reality. The stars are no longer out of reach, they're a destination waiting for us to explore. Thank you for joining us on this journey through the possibilities of artificial gravity. If you found this video as inspiring as we did, don't forget to share your thoughts in the comments below. What solution excites you the most? Which one do you think will shape the future of space exploration? Let us know, and if you enjoyed this content, be sure to like, subscribe, and hit the notification bell so you never miss out on more futuristic explorations. Until next time, keep dreaming big and looking up, because the future is closer than you think.